Okay, thank you very much. It's my pleasure to present. Actually, I have not much research result, but we are hardly work on how can we apply quantum computing to the computer-aided drug design. So actually this time it's a very practical and very short, very small, little thing, but it's very important in drug discovery. So title is the Can Quantum Computing Expand the Chemical Space for Drug Discovery? For drug discovery, there's a lot of problem in a patent because we develop drug based on the experience, so many of the chemical structure is quite similar. So it's very hard to escape from that kind of situation. So it's very important how can we expand chemical space and find new scaffolds for the new drug discovery. Actually, this is trend of it's the evolution of the computer-aided drug discovery and related technologies for computing. So computer evolution moved to supercomputer, now GPU, cloud computing, but now moved to the quantum computer. It works? Yeah? Okay. In the case of energy calculation, actually, for 50 years, we mainly used the empirical force field, now moved to quantum computing, quantum mechanics, and also people developed a neural net potential using the neural net networks with many potential energy surface data. But now we should use the quantum mechanics. I'll explain later. And also for the knowledge-based drug discovery, there's big data, deep learning, but now also use big data, but its generative model is quite popular. And structure, X-ray crystallography is the most popular instrument. Find the protein structure, but recently moved to the cryo-EM. Actually, this is the our technology, Baobab A-Bio. We equipped with those, but still a quantum computer is not active, but we're working on that. In the case of computer-aided drug design, there's two trends, big trend. First one is the knowledge-based one. Another one is the energy-based. Actually, starting from the energy-based modeling, but now many people move to the AI-based drug discovery, but still it's the most important because fine chemical structure and fine-tuning of binding. Actually, this energy-based modeling is very important. So recently, it's hybrided and so on. But people working on here, so quite few, because it's very hard to get a PhD, maybe 10 years for one paper, something like that. But here it's much better. And also many people working on here. So those two group people should prepare the good tools for drug discovery, computer-aided drug design. This is typical AI-based drug discovery. So if we have a data, for example, we have a mutant of mouse, mutants, and then we put some drug, then we check the efficacy or toxicity of animal. We collect data, it's a mutant activity, then we can put a future, for example, future of the drug, we change it to the number. It's a descriptor. So if we keep with the endpoint target and also descriptors, we can make this kind of function. This is the AI. For that, we can use artificial neural net and other machines, but recently AI, artificial neural net, is the most powerful. So once we get the model, we can check this model with experimental data, which is not included in the training. So we can check the model. This is the typical of the AI model. And also the most important part of the energy-based model is how can we accurately calculate the energy. So I think over 50 years, well, even 60 years, we use the empirical force field. Still is the most popular, but it has many problems because usually in the case of interaction, there's a multi-body effect is the most important. But in the case of this kind of empirical force field, they use only two-body effect, so it's a pair interaction. So they cannot explain this kind of multi-body effect. That's the reason why we should use the quantum mechanical energy calculation. If we can use the post-Hartree fork, that's the best, but the still limitation of computation, so we use up to this, or we develop people develop a neural net potential. It's very accurate. Its accuracy is quite near to this Hartree fork MO. This is drug discovery procedure. So there's many points we can introduce the CAD technique, but this time I want to introduce virtual screening for finding a hit compound. Actually, this is a report from the McKinsey. They said that there's many procedures for drug discovery, but especially this part for finding hit compound. The part is the most useful at this moment using a quantum computer. This is why we should expand the chemical space. So if we use the chemical library already existing, it means the compound plus the knowledge around that. But if we use that, there's a problem in novelty. So also, if we filtering with the additive properties, then only few success rate. But if we introduce like a molecular generator, they may have a novel scaffold. In that case, more novelty, and also if we introduce the condition for the additive for the generation, we can have a more high success rate. This is drug discovery procedure. So this is a procedure. If we have it's a virtual screening procedure, library, and the screening with the rough like filter, and then this is a more accurate filter using a binding, and then also check its additive properties, the screening. Usually we can get 5 to 10 compound for the experiment, but we think that this real library is not enough. So we should introduce the virtual library that includes much more novelty. So how can we generate this molecule? So this is a chemical. I think Professor Cho already introduced a number of the drug-like chemical space. It's a huge space. So how can we take chemical structure? What do you want from that big chemical space? So this is a chemical space. So it's estimate number of chemicals can be used for the drug discovery, but still we are at here. For generating novel chemical compound, if we applied for the restriction constraint like this one, those properties for good drug. So if we impose those kind of property during the generation of the chemical, then we can get the chemical compound that has a high probability of passing the drug discovery. So this is the strategy. How can we generate more novel and more high success rate chemical compound as a hit compound? This is an example of the generation of the molecule using Morgan, and another one is introduce quantum computing. So this is just a test. Some properties is improved, but still some properties not. So it's just test. It's from China. So for that, we can introduce this kind of property as a latent space. It's a constraint for generating. And how can we check whether it expands the chemical space or not? So there's a two way. First one is outside of territory. It's a external chemical space. I'm sorry. External chemical space. So also there's an internal chemical space. Even though we have a boundary of the chemical space, even inside there is a space we didn't explore. We didn't take a chemical structure from that space. So there's two kind of chemical space we should move out. This is the mainly used technique for generative model. This is very famous GAN reinforced running model, and this is a diffusion model. Those two models are quite popular for the molecular generation. Using that, it also from China. They checked the internal diversity and external diversity change when they introduced their quantum computing. So internal diversity, they much improved. And external diversity, some part improved. But if develop more better techniques, then maybe those value also much better than the classical computing. And also there's a benefit using classical computer. Actually there's a benefit in running effectiveness and running efficacy, and also they have improved the performance when we introduced the quantum computer for generating model. So the purpose of introducing a quantum computer is for the generation of the molecule is get the noble scaffold. And actually noble scaffold with desired properties. It's a purpose of the using a generative model. So actually this is a benefit. So we can have a much higher novelty and low risk. This is the purpose of introducing a quantum computer for the molecular generation. So actually, computer-aided design, we are here. So we are now in a NISQ state. So now we can use the quantum and classical computer hybrid machine learning model. Actually, there's a practical model at this moment, but we should move to the molecular mechanics using a quantum computer. For example, molecular dynamics and docking. So I think at the end of this NISQ stage, we can calculate this kind of, we can introduce that kind of model for the quantum computing. And finally, actually my dream is using a quantum computer for the quantum mechanics-based molecular dynamics. I think that's the perfect model. So that's my dream. Finally, I want to introduce the my university, Yonsei University, will install IBM quantum computer in this year. Actually, now we university prepare many things. For example, good researchers and also research centers, and so actually Yonsei University put a lot of efforts for quantum computing, especially one of the main topic for the research is the biology and computer-aided drug discovery and protein engineering. So I want to stop my talk at this moment. Okay, thank you very much.